our joint director, and the faculty of department and the faculty of other institutes, head of the departments of various departments of SJCE are already joined, and few more have to join, sir.
Great, good to see you all virtually.
Same here, sir. We are really honored to have you.
So we can start at 7:30.
Yeah, exactly at 7:30 we'll start, sir. Professor Roy, just to add, we are even giving the live link, and we are posting on YouTube also. Just in case if the participants exceed more than 100, because we have already got around 200 registration as of now. And this,
okay.
Yeah, so
No problem.
this is for your information too.
Sure.
Thank you, sir.
So, good evening, everyone. I'm Srimad Veera, Secretary of EDS IEEE-SJCE. Seeking the blessings of His Holiness Shri 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 Sivaratri Jayachamarajendra Swamiji, I would like to welcome everyone gathered here. We're grateful for this opportunity provided to us by JSS Science and Technology University and the IEEE Mysuru Subsection. Today, we have virtually gathered here for the lecture on Rethinking Computing with Neuro-inspired Learning, Device, Circuits, and Algorithms. So, on behalf of IEEE-SJCE, I would like to welcome the chief guest of the occasion, the speaker, Dr. Kaushik Roy, Fellow IEEE, Edward J. Tiedemann, Junior Distinguished Professor, Purdue University, USA. Welcome, sir.
Thank you. Thank you.
Next, I would like to welcome the Principal of JSS Science and Technology University, S.B. Kivade, sir. I welcome you, sir.
Thank you.
Now, I would like to welcome Dr. Jayachamarajendra, Joint Director, TED, JSS Mahavidyapita. Welcome, sir.
Thank you.
I would also like to heartily welcome Dr. M.N. Jayaram, HOD of Electronics and Communication Department, JSS Science and Technology University. Next, I extend my heartfelt welcome to the moderator of today's session, Dr. S.P. Rudraswamy, IEEE-SJCE EDS Staff Advisor, Commonwealth Fellow, Assistant Professor, ECE Department, JSS Science and Technology University, Mysuru. Welcome, sir.
Thank you. Thank you.
Next, I would like to extend a warm welcome to Dr. Sudarshan Patil Kulkarni, Vice Chair, IEEE Mysuru Subsection. Welcome, sir.
Yeah, thank you very much.
Now, I would like to welcome Dr. M.G. Veena, Branch Counselor, IEEE-SJCE Student Branch. Welcome to the talk, ma'am. Finally, a warm welcome to all the dignitaries, head of departments, faculties, industry professionals, and all the enthusiastic students who are gathered here. So, without further ado, I would like to call Dr. S.D. Rudraswamy to introduce the speaker to the gathering.
Thank you, Srimad. At the outset, I offer my humble pranams to the Guru Parampara of Suturmat, and it's really my honor and great pleasure to introduce today's speaker, Professor Roy. Professor Kaushik Roy is the Edward G. Tiedemann Jr. Distinguished Professor of Electrical and Computer Engineering at Purdue University. He received his BTech from Indian Institute of Technology, Kharagpur, PhD from University of Illinois at Urbana-Champaign in 1990, and joined the Semiconductor Process and Design Center of Texas Instruments, Dallas, where he worked for 3 years on FPGA architecture development and low-power circuit design. His current research focuses on cognitive algorithms, circuits, and architecture for energy-efficient neuromorphic computing, machine learning, and neuro-mimetic devices. Professor Kaushik has supervised 91 PhD dissertation, and I should tell here, and it is also honor for us that one of our EC alumni, okay, who passed out in 2007, was the PhD student of Professor Kaushik. So it is not that Professor Kaushik doesn't know about SJCE, but he knows already the SJCE. And his students are now well placed in universities and industry. He is the co-author of 2 books on low-power CMOS VLSI design. Professor Kaushik has received many recognitions and awards. Here are some of the recognitions and awards. Kaushik received the National Science Foundation Career Development Award in 1995, IBM Faculty Partnership Award, AT&T Lucent Foundation Award, Purdue College of Engineering Research Excellence Award, Humboldt Research Award in 2010, Distinguished Alumnus Award from Indian Institute of Technology, that is IIT Kharagpur, Fulbright Nehru Distinguished Chair, Semiconductor Research Corporation Aristotle Award in 2015, Arden Bement Research Award, which is considered to be the Purdue University's highest research award in 2020. And above all, he is a fellow IEEE. So these are some of the list. Along with that, he was also a research visionary board member of Motorola Labs in 2002 and held M. Gandhi Distinguished Visiting Faculty at Indian Institute of Technology, Bombay, and Global Foundries Visiting Chair at National University of Singapore. He has been in editorial board of many IEEE journals, and also he has won many best paper awards in all these things. So this is the introduction about the speaker, and without much delay, sir, it's again from the management side, from the university, from our college, heartfelt welcome to you, and the platform is yours, sir. Thank you.
All right, thank you, Rudraswamy, and thanks for the introduction. Well, let me try to see if I can share the screen first. Huh? Can you see my screen? Share your entire screen. It's somehow not happening yet. Let me check one more time. I think you have to give me permission. Somebody has to give me permission.
Okay, sir.
Whoever the host is. Huh?
Yeah, we will just,
Yeah.
just do that. We'll just do that.
Yeah, let me know when you are able to give me permission. I don't think I'm allowed to share at the moment.
We are on it. We are on it. We are on it. Sir, I think it doesn't require any permission. Can you just see whether your browser is asking the permission?
It's not, but it's not letting me share the screen. I mean, that's what I'm showing, but let me try something else.
Yeah, sir. You can see that right bottom you have present
tab. Let me see if I can share one of the tabs. Let me see. the present now is
Yeah,
one
now.
that I should use, right?
Yeah, present now, and then your entire screen.
Yeah, it's somehow not letting me do it here, your entire screen. And when I say share, okay, now it might, let's see if it works or not.
Okay.
Is it okay? Can you see
yeah,
the screen?
Yeah. So it's visible now, yeah.
Perfect.
Yes. Yeah, perfect.
All right, is it full screen now? Can you see it? Yeah,
yes,
all right, perfect. Yeah. Again, thank you very much, and sorry about all this confusion regarding sharing screen. But so what I'm going to do today is talk about some of the work that we've been doing in the area of neuro-inspired learning. And I'll go all the way from algorithms to devices, in particular, actually devices that can potentially do neuromorphic computing more effectively than the standard CMOS kind of devices. Again, I have a lot of slides, so I might not be able to go through all. So what I'm going to try to do is at least go over the initial part of this lecture. And a couple of other things, I know it's an EDS meeting, but I'm going to be starting with algorithms first, then go into a little bit of architecture and devices. So to start with, we all know that, AI has made a huge amount of progress in the recent past, right? And AI is all pervasive. It's all across different kinds of applications. If you really think about medicine, image analytics, transportation, customer, you name it, AI can potentially play a big role. But more recently, actually, in fact, a couple of years ago, IBM actually had this program and which could actually do debate. Interestingly enough, the computer lost to the debate. But it was actually very persuasive. On the other side of it, if you're really thinking about AI, the number of papers that are being submitted to some of these AI conferences are skyrocketing. If you also look at VC enrollment, that is going up. In fact, at Purdue, if I were to really look at the course enrollment for AI, that's also skyrocketing. So with that in mind, and as we can see that AI is making a huge amount of progress and AI is scaling, what are the problems? It turns out the AI compute demand can be really problematic. So if I were to really think about, for example, image classification or language processing, or take some of these optimization approaches, and training. In particular, if I were to look at NAS, which is a network architecture synthesis, what I'm plotting here is the number of operations required to, for example, train in NAS. And the number of operations turns out to be of the order of about 10 to the 21 for this network architecture synthesis. And that's really humongous. How humongous that is, if you're to really correspondingly look at the power consumption or the corresponding estimated CO2 emission from NAS, on and a big transformer, which is a big network architecture, turns out it's about 315x higher than air travel from New York to San Francisco per passenger. So the numbers are really mind-boggling in terms of the compute demands. On the other side of it, if you're to really think about the efficiency gap that lies in edge intelligence, and what we did is we did a case study on object recognition in a smart glass with state-of-the-art accelerator like the Google TPU, the Google Edge TPU. Turns out, and we actually implemented or analyzed RetinaNet deep learning network on a smart glass. It turns out, and our analysis shows that the time to die for the battery is just about an hour. And that's under ideal conditions. So if you consider all the non-idealities which is going to exist in circuits and systems of today, and then the battery life is going to be probably less than half an hour or so. So the question then, of course, comes is that where do these inefficiencies come from? And if you're to really compare that with, for example, the human brain, which is, we have an existential proof that it is reasonably efficient. In that case, the efficiencies we feel are coming from, not just the algorithms, but the underlying hardware architecture that is being used to implement some of these algorithms. And finally, the circuits and devices. So we'll go into each of those techniques a little bit later on. But one also has to understand that beyond the compute demand of AI, there are several other issues that one has to consider. And that includes, for example, today's deep learning requires a humongous amount of data to learn. So the question is, can I learn with less data? A few things which are also important, generalization and robustness. So I'm going to give you an example of the generalization on the right. For example, if my system learns a chair that I'm showing on the top, turns out, and then the question, of course, is if I give some test sets where the chairs look like what I'm showing here in the bottom, would my system recognize them as chairs and not as something else? On the other side of it, and that's a generalization problem, or really having accuracy of the system. And on the other side of it, what I'm really showing on the left is some images of an image of a macaw. Now, on the left is basically the clean image of a macaw, which my system, with very high confidence, say it's a macaw. But if I'm able to actually come up with some crafted noise, and I'm not telling you how to derive that noise, but it's possible to come up with some noise. And if I add that noise to the clean image of the macaw that I'm showing on the left, what you really get is what's on the right, which I'm calling it X-adversary. Turns out, and to the human eye, there isn't really any difference or much of a difference between the two images. At least to the human eye, we couldn't even make out any difference. But turns out my system now, with that noise, added noise, the macaw now is being recognized as, with a very high confidence, as a bookcase. Obviously, that's not true, and such things and some such robustness problems need to be addressed. On the other side of it, a few other things which are also important. I mean, today's deep learning doesn't learn in a continuous fashion. If I learn, for example, a particular task, a task A followed by task B followed by task C, today's deep learning is notorious in catastrophically forgetting the first task. So what's the way of learning then? The best way of learning today has been to really take task A, task B, task C, mix up all these tasks together and then learn, and then it turns out it's okay. However, it's difficult to do incremental learning. It's difficult to say, hey, I'm learning task A now. A few days later, I learn task B or task C. That becomes a little bit difficult. So there's a need to really think about doing something like what the brain does, really think about learning over time without really forgetting the past tasks that I've learned. And that's typically the problem that in the neuroscience community, people have been talking about, the stability plasticity dilemma, that, how do I really maintain accuracy while still learning over time and updating my weights accordingly? Now, I'm not going to go into any one of these techniques in detail. However, though we are working on each of those techniques as a part of a center that we have, Center for Brain-Inspired Computing. But today, what I'm going to be really focusing on is the compute demands, mostly on the compute demands of AI. Now, by now, it's hopefully clear that, in order to really develop proper machine learning systems or neuromorphic computing systems, one has to really look at the entire stack, going all the way from algorithms, which includes the learning algorithms, coming up with the right kind of network architecture, to the implementation of these algorithms or the network architecture on the right kind of hardware. And finally, at the end of it, we all know that CMOS has been the workhorse of today's technology. Now, they're certainly good as on-off switches, and certainly, again, using CMOS devices, you can build the right kind of AI hardware, but are they efficient? Is it possible to come up with the right kind of, are there devices which are better than the standard CMOS devices for these neuromorphic computing applications? So to that effect, looking at this entire stack, the question, of course, is, can I do a much better job than what I'm doing today with standard architectures and standard devices and this, standard learning algorithms of today? So the question is, can we take cues from the brain? As I said, we have an existential proof that the brain is reasonably efficient. So can we take any cues from the brain? And what are the cues that we can take in terms of the neuron model, learning algorithms, network topology, and the computing principles? So to that effect, and I'll go into a little more details of some of these things, turns out that there are different kinds of neuron model one can use. A more generic one that is the Hodgkin-Huxley model, But it turns out there are derivations out of these Hodgkin-Huxley model in terms of coming up with these leaky integrated fire neurons. There could be stochastic neurons and so on. The question is, what kind of neuron model should I use to have better learning? And is it possible to efficiently use them in a hardware architecture? What kind of learning algorithms? Today's deep learning usually use what's called the back propagation-based learning. I'll briefly talk about it. But also, localized learning has been observed, for example, in hippocampus of animals, and then such learning could be, for example, spike timing dependent plasticity and so on. So the question, of course, is, hey, should I really use such learning schemes? On the other side of it, how about the network topology? Should there be long-range connections in the network? Should there be feedback connections? Or should we also take some recent experiments that have been done, for example, mostly in the visual cortex of the monkeys, and in using that visual cortex of monkeys, is it possible to actually mimic some of these architectures? And then finally, what kind of computing principles should I use? Should I use communication and computation with spikes, as are really observed in the brain? Should there be a tightly integrated compute and memory? And we'll focus on that a little bit later on. Finally, what kind of architecture? Should the architecture be event-driven, asynchronous in nature for the hardware implementation? And what kind of input coding should I use? Should I have direct analog inputs coming out of, as an example, from the pixels into my system? Should they be coded in some different ways? Should it be rate coded? Should I have spikes which are based on times? Or there are different kinds of cameras which are coming out today, like the DVS cameras, and I'll also briefly talk about such cameras. Should I have inputs coming out of those sensors, those cameras, directly into my system in terms of spikes and so on? So that's basically the kind of cues that we can potentially take from the brain, and the hope is to build systems which are more efficient than what we get today, and at the same time, efficiency that we can be talking about are not just in terms of new learning, better accuracy, but also in terms of having energy efficiency. So let me get started. In order to do all these sort of things, let's first talk about the learning algorithms and the network architecture. And let's talk about the neuron synapses and the learning algorithms. So the neuron model, the first one to start with is a biological neuron that we might have seen, and then you basically have a cell body transmitting through axons into the next set of synapses and the post neuron, which is shown on the right. So in general, there are a bunch of input spikes which are coming to the neuron. And what happens to the membrane potential of the neuron is that goes up. And then if there are no spikes, then of course the membrane potential actually sort of leaks a little bit. And then if there are more spikes, when it goes beyond a certain point, the membrane potential goes up beyond a certain point, beyond a threshold voltage, let's say, then the neuron switches, you reset the neuron in some ways and start operating again. And at the output, you actually end up producing a spike. So that can be very well represented in terms of these, leaky integrated fire equation using, for example, an RC circuit. On the other side of it, I mean, this is actually, you can say it's a little bit complex model. If I don't want to use, for example, a leak, as I was showing in the previous case, what one can also do is that, hey, I'm not going to have the leak part to it. I can potentially have an integrated fire neuron, and the integrated fire neuron is going to behave, again, similar, but not exactly like the leaky integrated fire neuron, as I'm showing on the red on the right side of it. It also tells you is that you're probably going to have more spiking activity. And then finally, one can also think of, I mean, there are other kinds of neuron models, but the other one that is also kind of interesting and we've been looking at is a stochastic neuron model. So in other words, the neuron switching function or the transfer function looks somewhat like this, which is shown as a sigmoid function. And rather than just being it a sigmoid, if we assign a probability to that sigmoid, in other words, if I have a switching probability, if the input to a neuron comes in and the neuron switches with a certain probability, and the probability of switching is shown by the sigmoid switching curve, it turns out it can actually do interesting learning, not just for the neurons, but such kind of stochastic learning is also possible for the synaptic devices. Going further, and so far we talked about the neurons. The question, of course, is, hey, how do I do synaptic updates? As I mentioned earlier, one of the ways of learning would be, localized learning. And there's been a good amount of experiments done, in particular, actually back in 1990s, where Bu and Pai showed something, a learning mechanism, which is a localized learning mechanism, which is called spike timing dependent plasticity. The learning mechanism can be used, or at least understood quite easily. If I have, for example, what I'm showing is a output neuron O1 and a bunch of input neurons I1, I2, I3, which are connected through weights W1, W2, W3. So now let's say that I have a situation where I have a bunch of inputs which have come in, which is shown by I1, which is a spike at a particular time, I3, another spike at another time that has come in. And due to these spikes, what has happened is that the output has spiked. The output neuron has spiked, which is shown in red at the output. Now, obviously, by looking at this, you would say that the output spike was generated mainly because of I3, because the timing difference between the output and the input spike is the smallest in that case. Did I1 play a role? Certainly it also played a role, but not as much as I3, right? So to that effect, you would like to say that, hey, if I have to do the updates of the synapses, then I3 should play a more important role. In other words, the weight W3 should play a more important role, and it should be potentiated more than W1, right? So to that effect, based on some of these experimental evidence that was shown, what one can say is that I'm going to update W3 based on, the post-neuron spiking time, which is T-post minus the pre-neuron spiking time, which is T-pre. So T-post minus T-pre basically tells me how much should I update the weight by. And it's kind of a Hebbian learning. And so how much is the weight update going to be? The new weight Wi is going to be old weight plus some delta W. And that delta W change is a function of T-post minus T-pre, as I mentioned. Now, on the other side of it, if you really think about it, nothing happened to I2, so I don't need to do anything to I2. However, if I do have a spike that comes in later than the neuron has spiked, then he said that I2 did not play any role at all. In particular, actually, since the spike came later, I would actually depress the weight. So to that effect, rather than potentiating the weights, I would end up depressing the weights, and this follows completely the Hebbian learning. However, there are different kinds of modifications of these, STDP learning that one can use. There are different kinds of, single-sided STDP, which is not completely Hebbian. Part of it can be, anti-Hebbian too. Or people have been using also reward-modulated STDP and other kinds of learning mechanisms. So we'll see that, how some of these mechanisms can be useful for, learning, in particular, actually, in a smaller scale for STDP. There are other learning possibilities. So rather than localized learning, the standard deep learning community uses, the back propagation-based global learning. So what that learning mechanism is really that if I have a neural network, which are showing on the left, and if I have a bunch of inputs which are coming in, and if I'm showing, for example, a cat to the input, a cat, pixels of the image of a cat to the input of this network, then the output is supposed to show and tell me, hey, it is a cat. However, if it doesn't, if it says something else, what you can really say is that, hey, the output is different from what I'm supposed to get. So what I'm going to do is there is going to be loss at the output. Instead of a cat, it says it's a dog. So there is a loss function at the output. So if I now back propagate that loss function to the circuit, to this network, I try to figure out what weight I should have in order to really make a cat to be a cat and a dog to be a dog. So this back propagation basically helps me in determining that. Now, back propagation requires that I have to calculate the gradients of the functions, in particular, actually the activation functions and the outputs. And it's possible to do that effectively in a standard deep learning network because of the analog nature of the input and the output. However, the inputs and the memory potential are discrete in nature in case of spiking neuron. So that would require, for example, making some approximations for the calculation of these gradients. And one can use different kinds of, these are called surrogate gradient techniques that one can use to actually train these networks. So certainly possible to use both synaptic learning, localized learning, like STDP as an example. It doesn't have to be, but it could be other global learning also possible, like backpropagation-based learning. So with that in mind, I'm gonna quickly talk about what can I do with such learning scheme. One way of looking at it is that, let's say that I want to fly a drone. Now, and if I want to fly a drone, for example, in a GPS devoid environment, so just by vision sensors only, if I have to fly a drone, then what are the requirements? First of all, one has to actually predict the optical flow. The second thing that is required is that I need to do some sort of a depth estimation. And finally, you have to do the object recognitions so that I can avoid obstacles and fly. So to that effect, the first thing that one can look at is a very simple example of an optical flow estimation that one can do. Now, what kind of input sensor should I use? One can use a standard camera. Now, that's good, but today there are other kinds of interesting cameras that have been developed, and these are called, event-based cameras. So these cameras would actually produce spike as inputs. Now, why is that important? Turns out that when there's a relative motion between the object and the camera ends up producing from each of those pixels, spikes. I'm not going to the details of it, how it's produced and what kind of spikes are produced, but for the timing, it suffices to say that it'll end up producing the spikes if there's a relative motion between the object and the camera. Now, if there is no relative motion, then of course it doesn't produce any spikes, and it goes into this, completely low power mode. So if there is no, a motion, of course, and there's no relative motion, then there's not going to be any spikes. So if those spikes are basically the events, and out of those spikes, the question, of course, is, hey, is it possible to generate the optical flow? Now, you might say that, why am I not using a standard camera? Now, it turns out that you can also use an standard frame-based camera for doing optical flow, but it turns out it's not going to be as accurate as some of these cameras which have higher fidelity. A few other things, these cameras are extremely low power. As I mentioned, that if there is no motion between the camera and the object, there is not going to be any spikes that are coming out. Now, since there are spikes, it also tells me that I have to really come up with a network, which is, it's going to be better if I come up with a network which can handle spikes rather than analog inputs. And to that effect, basically, here is a proposal of a network which is not just the standard, which is not standard deep learning, but it has a front end, and there's a reason why I'm using a front end to be a spiking neural network. But interestingly enough, the back end is actually a standard analog neural network. And the reason, without going into the details of it, why such a hybrid network is used is because the inputs are very suitable for effectively being used as an SNN. And one can potentially do event-driven computation and can potentially get improvement in energy. However, spikes are rare. And as you go through the network, the spikes do die down. So in order to sometimes learn better, it might actually be better to use an ANN in the backend. And to that effect, actually, some of these inputs that are coming out of these SNN or the spiking neural network block is actually accumulated and fed into an ANN block, and the reason really being the fact that it's possible to get slightly better accuracy in a hybrid network like that. So with that in mind, actually, we developed this, trained the spiking neural network using the techniques that I talked about. Similarly, you also trained the ANN using a backward propagation-based technique. And what I'm really showing here is a real-time optical flow prediction, where in this particular case, in front of the DVS camera, my student is walking, doing all kinds of things to really show that, hey, I can get a predicted optical flow, which is reasonably good. And coming out of these, new cameras. Let me go back and it's possible to do that, and this is also do this optical flow, for example, in the streets of West Lafayette in our campus. So it's directly showing that, just using these cameras, one can actually do different kinds of optical flows. And what's good about it, the reason why SNNs are used and these event-based cameras are used, it actually gives you, in a way, better accuracy. And the reason why the better accuracy is come because, we can effectively use the membrane potentials of these, new spiking neural networks. And at the same time, the energy efficiency of this system is actually much better than a standard ANN-based system that one can use. Now, going a little bit further, one can also do, for example, a few other things using these DVS cameras. One can do gesture recognition. And this is where I'm showing an LSM. LSM stands for a liquid state machine. It's basically, again, a neural network, a spiking neural network, which has a random set of connections. There's some excitatory neurons which are connected randomly. There's some inhibitory neurons which are connected randomly. And the output of it is actually trained using spike timing dependent plasticity-based learning. So it's a little bit different kind of learning that I showed earlier. And the idea is to actually recognize gestures coming from the DVS camera. And here again is my student actually showing that, hey, the camera which is shown in the red right here is basically being, given the gestures, and in real time, basically the drone then decides, hey, should I fly up? Should I fly down? Left, right, and so on. So these are different possibilities that one can do. Again, the basic idea is that if you do it effectively, you can actually get better energy efficiency, and at the same time learning with these new sensors, which are also quite energy efficient. Again, going left, right, and top, down, and these are the kind of gestures one can potentially do. And obviously, you can do other things. Now, let me switch gear a little bit and try to see, we talked a little bit about these learning algorithms. And the question, of course, is that what kind of hardware should I have? What kind of circuits and devices that can potentially be used to really, make these systems, learn better? The obvious question is that, hey, can I use the GPUs and the CPUs for effectively doing, implementing these learning algorithms or these network architectures in them? Turns out that while GPUs are certainly good in terms of doing matrix multiplication, which are one of the important, computational elements that are required for deep learning, turns out they may still not be very efficient in doing event-driven computation. There's several other things that need to be considered. The problems of using a standard von Neumann computing architecture, and secondly, and a few other things. So the question then, of course, is the fact that, hey, what kind of hardware fabric should I use? So today's hardware fabrics, as I mentioned, are multi-cores, GPUs, and accelerators, which are shown in the bottom. Now, are they good? They're certainly, doing a reasonable job in terms of, standard ANNs, but the power consumption, the latency is still large. So the question, of course, is that can we really come up with new, take these algorithms and implement them in a hardware that can embody the computing principles of the brain? So in other words, if I really think about the brain, there isn't really a compute unit on one side and a memory on the other side. They're all, jumbled together in some ways, and the computation in a lot of ways are done in the memory itself. So if I look at the standard von Neumann architecture, you might have heard of what's called the memory wall. The problem is that when the memory, when you keep going to the memory, fetching data from the memory, doing the computation of the CPU, and then you give it back to the memory again, it turns out that actually that traffic into the memory actually is a big bottleneck. So question, of course, is can I get rid of that bottleneck? The second thing also that is also important is that, for SNNs, we talk about matrix vector multiplication, but for an SNNs, you might actually be able to just do with the accumulation and no multiplication. Can I take advantage of that? Thirdly, if you really think of all these systems that I'm talking about, right, they are in a way error resilient. So if these systems are resilient, is it possible that I do some approximate computing? In other words, my hardware may not exactly do or maintain the exact Boolean equivalence. And if I don't maintain the exact Boolean equivalence, then what should I do? I mean, should I do it just for the fun of it? It's actually kind of interesting arithmetic to play with, where you don't maintain the Boolean equivalence and still able to get the result that you want, because these are error resilient systems. But also at the same time, the idea is to have low complexity logic to be able to actually do, have lower power consumption. At the same time, if you are able to do, stochasticity I mentioned, I'm not going to be going to the details of that, but can I use a stochastic hardware? Event-driven computation, and finally the devices that I end up using, can they be devices that can potentially directly mimic the neurons and the synaptic functionalities, rather than using standard CMOS devices. It's very difficult to get rid of the complete standard CMOS devices completely, but can I really use some of these devices, the non-volatile devices that there's a good amount of research going on, to be able to actually use them effectively for neuromorphic computing? So in other words, can I really think of devices that are neuro-mimetic, or can actually do these operations in a very effective way using the new technologies? So let's look at some of these technologies. On the very left, I'm showing a ferroelectric transistor. So why are ferroelectric transistors interesting? It turns out some of these devices can potentially be used as a synaptic and a neuronal device. It's also possible to use other kinds of magnetic devices. You might have heard of other kinds of RRAMs, the resistive RAMs, or the PCMs, phase change memory kind of devices. So all these devices it's possible to use. They're quite colorful devices, both literally and figuratively, as shown there. But it turns out that some are a little more mature than the other ones. So one can potentially look at RRAMs, PCMs, or in fact, some of these magnetic tunnel junction-based devices that can potentially implement directly a neuronal functionality or the synaptic functionality. So what's important for the synaptic functionality? We need to be able to actually implement, different, and these are all non-volatile memories in some ways. So to be able to actually have the synaptic weights to be implemented using these devices. Can I use synaptic weights and different synaptic weights? And they can be analog in nature, but hey, can they be storing different bits in these devices? Similarly, is it possible that I can put them in such a way, and I can arrange them in such a way that I can do some computations in the memory itself? Remember, I said that there's a memory wall, so it's possible that I do some of the computations in the memory itself. One can certainly also use magnetic tunnel junctions. They can store only logic 0 and logic 1, but in a lot of cases, it turns out logic 0 and logic 1 might be good enough. There are several other issues one has to look at before you're able to use these devices. So let's try to compare some of these devices with CMOS, or standard CMOS SRAMs, the memory. So if I have to really focus on certain areas, let's look at the cell area. The cell area turns out to be, for a PCM RRAM, it's quite small, 15 to 16 F squared. Whereas on the other side, a magnetic tunnel junction, probably a little bit larger. But if you go to the CMOS, depending on the kind of CMOS SRAMs you're using, 60 or 80, they can be quite large. Write energy, turns out for these PCMs, RRAMs, they're quite large. MTJs are certainly larger than CMOS. Write latency, similarly, you can follow the trend. CMOS certainly is quite a bit better. But more importantly, if you really think about it, the endurance, the read endurance and the write endurance of PCMs and RRAMs are not as much as the standard CMOS, CMOS and the MTGs. So what it also tells you is that while the PCMs and the RRAMs have low area, endurance is a problem. And if endurance is a problem, one has to really think of the right kind of architecture. Can you use it for training, which requires a lot of write? And should you just use it for inference, or should you use it in some other ways? Do become important. So as I mentioned, I'm going to be now focusing on some of these architecture and try to see, if we can use some of these devices to actually do the computation better, faster, and in a more energy efficient fashion. So to that effect, one can look at in-memory computing. And why is in-memory computing so important? I mentioned about the von Neumann wall. And if I'm able to do the computation in the memory or close to the memory, then certainly I can get rid of or overcome some of these von Neumann bottlenecks. Different ways of doing that, and I'm going to go into that. But before I go into that, it turns out that if I look at, for example, a TPU floor plan, almost 60 to 70% of the area is really taken up by memory. So it does make sense to really make the memories more efficient and do the computation in the memory. A few things. How do I do the computation in the memory? We are all familiar with, for example, the standard 60 cells are the standard memory. And what one can do is, in a typical memory, we turn on one word line, and there are corresponding peripheral circuits to do that. And this is the standard memory operation. But rather than using actually, turning on one word line, is it possible to turn on two word lines simultaneously? Turns out it's possible. It becomes a little bit difficult in a standard 60 cell because there's going to be a path from VDD to ground if you do that. So, but in 80 cells, it's possible. Only in the read part of the circuitry, you can turn on two word lines simultaneously. But of course, the kind of memories that I'm going to be talking about, it's possible to do that. And by changing your sense amplifiers and your peripheral circuitry a little bit, turns out it's possible to do different kinds of AND operations, NAND operations, or OR operations, or XOR operations. Going a little bit further, if I can I turn on multiple word lines simultaneously? And if you're able to do that effectively, turns out you can do vector matrix multiplication. And again, you need a little bit more peripheral circuitry to do that. Various ways of doing it using non-volatile memory technologies. Question, of course, that comes up, and I don't think I'll have any time to talk about it, but it's possible to do that also in SRAMs. The problem with SRAMs is the area is going to be large, right? But with some of these non-volatile memory technologies, it can be much smaller. I also won't have any time, but it's possible to sometimes embed a ROM into a RAM at no extra cost. So you can potentially think of having an 1 MB RAM, and along with that, an 1 MB ROM. And the ROM can potentially store different kinds of neuronal functionalities, and the RAM directly can store the synaptic weights. And if you're able to do that, turns out you can actually do effectively fast computation. So to that effect, I'm basically showing a crossbar kind of architecture where these these devices that I'm showing in orange or pink are really the devices that are like this NVM technologies using, for example, MTJs or PCMs or RRAMs. And if I were to really look at this array that I'm showing, that array basically has a bunch of inputs, as I mentioned earlier. If you're thinking of having an RRAM or a PCRAM or an STM RAM, you can potentially have an access transistor, the access device, which is shown here, and the device itself along with that. And if you were to turn on these multiple word lines together, which are shown as V0, V1, Vn, what you get at the output is basically, using Ohm's law or Kirchhoff's law, what you get is the output is I, the current, which is going to be a summation of Vi, which is the voltage of the input, times Gi and Gijs, which are the conductance at each of those nodes, right? So in other words, if you really think about it, we're doing a matrix vector multiplication, right? Vi times Gijs, summation of that. So using, and these are the two terminals, selected devices or a transistor as access transistor. You need a few other things. You can potentially think of having these MVM, the matrix vector multiplication unit, which are required for these neuronal functions or the synaptic functions. The synapse stores the weights, and the neurons end up doing basically the weighted summation of Vi times Gi. And so once these are done, you can put a bunch of them together into an network on a chip kind of architecture, connected through some switches, and they are communicating with each other to implement basically your neural network. Few things don't come for free. There are a few things that are going to be required. While effectively you're able to do these in-memory computation, the communication between these MVM units have to be done, and they better be in, for example, using these, NOC kind of architecture. But the communication in general, you'd like to do in digital domain. So you don't want to add up errors. Now, if you want to do the communication in the digital domain, then you need A to D converters. So in other words, if you can potentially think of A to D converters, and again, the outputs of these A to D converters, they'll feed into these next, MVM, and so you need a DAC, digital to analog converter. So those are required. So one can potentially think of an architecture, and if you're interested, this was actually a work presented earlier in 2019 in an architecture conference called ASCLOS, where we looked at this architecture where these cores are basically the ones that I talked about in the previous slide, which are really this MVM, matrix vector multiplication, along with some extra circuitry in there. And these are connected, and there's also a need for some shared memory to do some other kinds of operations that are required for the neural network. So one can think of an architecture where a bunch of these cores together would form a tile, and some of these tiles are going to be then connected together into a network on a chip architecture. I know I don't have much time, but a few things which are also important, that as I mentioned, that the MVM unit is going to look somewhat like this, which is basically a matrix vector multiplication unit with the inputs coming in from the digital to analog converters, because they're coming from other MVM units. The output of these MVM units is going to be analog values, so they're going to be converted using an analog to digital converter. Few things which are important is to also remember that each of those devices, as I mentioned, are analog memories. So how many bits do they implement? If I'm thinking of implementing as a 4-bit device, if the device has to be 4 bits, and if I'm not able to implement that as 4 bits, then each of those devices can be, if they're 2 bits as an example, then I need to do some weight slicing. Or in other words, 4 bits can be implemented using 2 crossbars. Similarly, the inputs can also be, while the weights can be sliced, the inputs can be also bit streamed. If the input, as an example, is 5, I can bit stream the input as 101. So using bit slicing, bit streaming and weight slicing, it's possible to actually use low precision crossbars with low precision DACs to get high precision matrix vector multiplication units. Now, why is that important? It turns out the cost of doing the computation is really dominated by the ADC cost, analog to digital converter cost. So the size of the crossbar array, whether it should be a 128 cross 128, should it be really 1 bit, 4 bits, how many bits should they implement, really depends on the accuracy of a few of the things, in particular, actually the analog to digital converters. And your power consumption is going to be dominated by that. So even though you're able to now save in terms of doing computation multiplications in the memory itself, you still have to worry about a few things. Hey, how do I do the computations, and how do I reduce my cost of the A to D converters? So I'm not going to go into the details, but very quickly, and I know that I'm running out of time. What one can do is, for example, multi-layer perceptrons using the cores that I showed earlier. I'm supposed to be doing then Z is equal to MX, which is matrix vector multiplication, followed by a neuronal operation. I'm showing it to be a sigmoid function that I do. So my multi-layer perceptrons can map into one matrix vector multiplication unit. So we use stores, load, MVM, ALU, and stores. But a few things which are important, without going into the details of it, it turns out that each core has, let's say, a 128 cross 128 crossbar or a 64 cross 64 crossbar. But if your matrix multiplication requires that you use, larger crossbars, which you're not able to use because the ADC cost goes up, you might need multiple cores, and not only multiple cores, and you have to take the partial sums from one and then accumulate the partial sums so that you're able to combine it from different matrix vector multiplication unit coming from another core. And so larger matrices would require more data movements to compute the effective matrix vector multiplication. I'm not going to go into the details of it, but I just wanted to show something which is kind of interesting. The NVM macros there are several non-idealities. And these non-idealities come from the fact that there is going to be resistance or on resistance or off resistance of these devices. What's the difference between, what's the ratio of R on and R off of these devices? There is going to be resistance on the lines. There's going to be source resistance, sink resistance that you have to really look at, and the variability. So to that effect, I mean, there's going to be a good amount of variations. And at the same time, you have to also think about, how large a crossbar I can use. And if I do use a large crossbar, it turns out from the point of view of energy efficiency, might be able to do better, but my accuracy of the system might actually go down. So selecting the right crossbar size for energy efficiency and accuracy turns out to be quite important. And a few other things I also wanted to mention, that your energy efficiency is now, energy consumption is dominated by the energy of the analog to digital converters I'm showing at the bottom. And similarly, the area of the crossbars are really low, but the peripheral circuitry, which is basically the ADCs, would end up taking a lot of area. Again, there are ways of emulating the non-idealities of the memory stick crossbars. I'm not going to go into the details of these. There are papers on it that we have published, but I may not have time. But what I really wanted to show, there's several architecture challenges we still have to look at, even though you're doing in-memory computing, which basically alleviates the memory wall bottleneck. You still have to worry about sending data between different cores or between different tiles, and that communication cost has to be considered. And if you do all those, you're still going to be able to get a large amount of improvement compared to, for example, a standard GPU. So here are some results showing that if you are to really look at the GPU implementations, Skylake, Pascal, and compare that with the proposed architecture that I talked about. And this is a simulation of Puma. The devices that we ended up using are basically the devices that we got from, or at least models from HP. And what it really shows at the end of it, looking at MLP, which are multi-layer perceptrons, deep neural networks, wide neural networks, CNNs, which are convolutional neural networks, or in fact even LSTMs, the RNNs, which are the recurrent neural networks. LSTMs are those. Turns out it's possible to get a huge amount of improvement in energy consumption. And that's something which is kind of interesting and important, that even though your area is dominated by these ADCs, even then, if you're effectively using these architectures properly, you're able to get 100 to 1000x improvement in energy in a lot of cases. So what I'm going to do is, I know that I'm running short of time. I just wanted to mention that it's possible to use CMOS technology for in-memory bitwise vector Boolean operations, MVMs, and so on. I don't have the time to go over the CMOS, but CMOS certainly can be used. It's going to require larger area, but it has an advantage of endurance and low write power consumption. So while it is interesting to look at some of these interesting technologies that I talked about, endurance in RRAMs would play a role. Even though they are small, you need to think of a spatial architecture without a DRAM. With SRAMs, you can potentially think of an architecture where you can also have a DRAM, but the area taken up by the memories is going to be quite a bit larger. And similarly, STT-MRAMs are somewhere in the middle. They have higher endurance, not a good R on to RR ratio, but certainly can be with sparsity, if you consider sparsity, can be usable, and because they have a much higher endurance, and we can certainly have a DRAM along with it. So I'm not going to be able to spend more time. It's possible to do such computations in the DRAMs itself, in-memory computing in the DRAMs, but I'm not going to be able to, again, as I said, go over it because of time. I intentionally put in a lot of slides, but I knew that I wasn't going to be able to finish everything. So here's some parting thoughts. Bioplausible networks and spike-based information representation. That's what I really focused on today. Can potentially give you energy efficiency and robustness. These are the primary advantages at this point. I also believe, and I didn't go into much details of it, the temporal domain is the key. Are we using the temporal statistics in the best way to learn, sequential tasks using these spiking neural networks, which basically the standard, DNNs would have a little bit harder time to do. They have certainly potential for edge computing, in particular, actually using low power sensors like the DVS cameras that I talked about. And then I also, briefly talked about these neuro-mimetic devices. I know I didn't go into the details of these device operations and technology, but I basically talked about how they can be used to really effectively use at synapses and neurons, and in particular, actually to do in-memory computing. And that can potentially give you a large improvement. Finally, as a parting note, I believe that algorithm hardware co-design, guided by biological principles, can be a pathway for the next generation of neural computing. So that's all I have. Sorry, I have taken a little bit longer than what I should have, but I'll be happy to answer any questions if you have time.
Yeah, thank you, Professor. So it is exactly 8:30 now. So thanks for giving information on how exactly the classical devices along with the non-classical devices are used in building up the circuits, the algorithms, and also taking us to the state-of-the-art work on rethinking computing with neuro-inspired learning, especially the memory and all. So it was really a nice presentation. I hope most of the participants have enjoyed your talk. So now, anyhow, so there are some couple of questions that have come up. So can I take, Professor, so that you can?
Sure, please.
Yeah. So I have the first question by Professor Shashidhara HR. So he is a faculty at one of the other engineering college at Mysore. So his question is basically how a neuromorphic computing developed using quantum devices and memristor devices.
Okay. I assume the quantum devices that you're talking about are basically, I'm not talking, first of all, let me be very clear, I'm not talking about quantum computing here. It is not quantum computing, it's neuromorphic computing, using still the standard devices. Magnetic tunnel junction uses, for tunneling, it uses an thin oxide layer, but it's still not used in this particular case. The spin is not used as a quantum computing device. That's one thing. Certainly, CMOS and other kinds of technologies can be very well used. And I couldn't go into the details of CMOS, but you can certainly do a crossbar with CMOS. You don't have to. You can certainly still go with a von Neumann computing scenario, which is going to be not quite effective in terms of energy consumption. But certainly that's what we do today. And the crossbars using some of these non-volatile devices that I talked about can potentially mimic, as I said, effective synaptic operations. Synaptic operations are certainly more important in some ways than the neuronal operations, meaning thereby that there are a lot more synapses, probably about 10,000 times more synapses than the neurons or so. That doesn't mean that we can ignore the neuronal functionality, because that sort of gives you the learning, but you can potentially have the size of the neuron and certainly can be a little bit larger than the synaptic devices that we can have.
Yeah, so we have one more question from Shashidhara, but anyhow, so we are giving a chance for other participants. So we have other question from our joint director is asking, can this technology be implemented in semiconductor or quantum computers?
Semiconductors computers, as I mentioned, I didn't go into the CMOS part of it. Absolutely, it's done today. Absolutely done today. Effectiveness is what I'm talking about. So certainly can be done, no question about it. Quantum computers, I'm not really, people talk about quantum AI. And there are various definitions of it. I mean, how you want to look at it. Can I effectively use the quantum computing framework to implement or make things faster? Which is still a very, very open problem. Don't know, people don't know exactly how to effectively do that, but there are some interesting possibilities. If you're talking about building quantum computers or building quantum devices which can potentially, or the materials, exploring materials using some of these machine learning techniques, that's certainly possible, and a good amount of work has started in earnest in such areas. But I'm not going to be really talking about quantum computing as separate. that, superposition and other kinds of requirements that are required for quantum computing is not a requirement here.
Okay, thank you. So we have a question from one of the students. Sir, according to you, how far are we in time from witnessing combination of hardware and software as powerful as real human nervous systems?
I think we have still a long way to go, right? We don't have the biological neurons. We don't have the biological synapses. I mean, building those, we don't have it, and we don't even know the learning algorithms quite well. So there's still, to tell the truth, a long way to go.
Okay.
There's still a huge amount of gap in terms of what we understand about the brain and what we're able to implement. And what we are implementing in this particular case is that we don't have certainly have the neuronal devices or the synaptic devices, biological devices. We don't have the GUI nature of the brain. We don't understand a lot of these things, going from learning algorithms to the hardware of the brain. But the question is taking cues and trying to go as far as possible to see if we have the efficiency. So if I have to really put it, bluntly, the idea is to really look at bioplausibility is not really as a means to is really a means to an end of achieving, energy efficiency. To try to see if we can do better learning. It's not be all end all.
Okay, so we have one question from our professor. Can we implement kernel functions like the ones used in SVM or wavelets using these devices?
You can do different kinds of computations, but the thing is that most of the time when you're trying to use, for example, these deep neural computing, deep neural networks, if you're able to something you can mathematically model well, and if you know how to do that using the standard signal processing techniques, probably you will do it. Can I implement an XOR function in using, for example, a neural network? The answer is yes. But should I? That's the question, because I can do it more effectively using other means. So the problem has to be right? And there are certain problems which are well suited for it, where we can play with the data. We're not able to model it very well. So playing with the data and learning certainly helps. And in some other cases, it doesn't make sense. There are applications where it also doesn't make sense. You have to think about, we can always find some sort of a correlation and in the data itself, and the correlation does not necessarily mean causality. So causality has to play a role in a lot of, some of these cases. I can potentially think of, if I remember correctly, there was some controversial things which are also being done, right? For example, looking at facial expressions of people, you might be able to say that, hey, you can collect some interesting data out of it and say that, okay, this is related to this versus that. Is that fair? Is there a causality? Probably not. As such causalities are, until it's shown properly, it can be misused and misused in a really bad way. So one has to be careful about where to apply it. But certainly, if the problem can be modeled well mathematically and can be solved better using standard machine, I think one should do that, rather than taking, a neural network to implement that problem. Does that make sense?
Okay. So we have 3 more questions. So can we take them?
Sure. Yeah, no problem.
We have one from Dhanush Srinath. Considering the recent event of a monkey playing a video game, what are your thoughts on how complex and time-consuming it will be for such innovations to go further on humans?
Such innovations, meaning we'll try to play. We know how to play video games, I think. But you're talking about games that we can't play. As you can see that, these days people are learning from the, chess. If you are probably a grandmaster, you're better off playing. I mean, if you're really good, you're better off playing with a machine than with another human in some ways. So you can probably learn better in some interesting ways. I mean, it's almost impossible to beat the computer today. If you're talking about games like chess, games like Go. Go is even more complex. Interesting things are happening.
Okay. Yeah. So next question is from Karthikeya Joyce, a student. Considering the computational requirements required for AI and ML, what are your thoughts on tiny ML?
That's certainly a buzzword that is being used quite a bit these days. And, I call it microintelligence. Some other people would call it with edge intelligence, right? Absolutely important. And if you really need to put intelligence everywhere, and you really need to think about, architectures which are, reasonable. By reasonable, I mean the energy consumption is going to be what some of these, edge devices can handle, right? So energy plays an extremely important role. You may not need to solve, very, very complex problems, but the problems as you suit as to what you're supposed to do. Can you distribute them in some very, exciting ways? And not only that, I mean, distributing intelligence turns out to be quite important, so that we can, one can collectively learn in some fashion. One example could be flying drones again, and the drones can explore different areas of a particular room in a GPS devoid environment, and then they don't have to go everywhere. Using some learning techniques, I mean, distributed fashion, they can collectively learn in some ways with the least amount of communication as possible, because again, communication cost is going to be large. So absolutely, it's while it's machine learning, but at the same time, for such things, it's energy.
Okay. So I think we'll go with the last question. So anyhow, so I'll share Professor Kaushik's email ID if you want to still want to discuss on the current trends, or what are the probable things that UG student can do in this post-graduation or the thing. So we'll take up the last question. Are synchronous models better for large data or the ones we just discussed?
Again, a good question. I mean, people have been talking about, I assume that you're talking about when I talked about event-driven computation, synchronous, or should I do event-driven asynchronous computation is the question. A lot depends on the kind of hardware that you have to be able to do effective asynchronous computation. Even though in some cases you can get improvement in energy consumption, if you're not required to do much of handshaking, but if a good amount of handshaking is required, that can potentially be an issue. Going back to the standard issues related to that becomes important. So you probably have to do a less complex event-driven computations and so on. That might actually make more sense. I don't know if I did answer your question, but it's a problem of the standard problem I feel in the hardware domain of synchronous versus asynchronous, how much of handshaking is required to do asynchronous computations, and but if I can make some approximations and really go with a little bit less stringent constraint, can I do computations more effectively if my spikes, as I was talking about, are rare and there's a huge amount of sparsity? It doesn't make sense to do probably completely synchronous computations in a lot of ways. But still, one can use a clock in some effective ways to bring some sort of synchronicity, so to say, in the computation.
Yeah, thank you, sir. And once again, I thank for your valuable time sharing with us, especially the young personalities at our institute and also in India. So I hope your talk, 1 hour useful time, this motivates and also inspires students to take up the new challenges in their academic career. So thank you very much, and we are really grateful and honored to hear you, and also very much time for sharing 1 hour time with us. Okay, so this is really we are very lucky, and also we are honored to have you, sir. And coming to the end of this session, I think back over to the Execom members, sir. We have a couple of formalities. Okay, so I think then we will wind up the things. It will not take more than 2 to 3 minutes. Yeah, thank you.
No problem, man. Thank you very much. I certainly enjoyed giving the talk. So.
Thank you,
and
sir.
Thanks for all the questions. Yeah.
Yeah, thank you, sir. So anyhow, some of the questions will be coming to you over a mail and all. Okay, so anyhow, after sharing. So yeah, so now I give it back to the Execom member to just carry out with the further proceedings. Thank you.
All right. So thank you very much.
Yeah.
Thank you, sir. So, now I would like to call upon IEEE-SJCE's Editor-in-Chief, Varsa Alia, to release the annual IEEE magazine.
Sir, I'll take this permission from you that IEEE-SJCE especially releases an annual magazine every year, and so I request, and this will be once again an honor for us that virtually you will be releasing this particular magazine for us.
Okay.
Yeah, please, sir. Ashima.
Yeah,
Hello, everybody.
Yeah,
okay, yes, okay. Hello, everybody. I am Varsa Alia. I'm the Editor-in-Chief of the SJC Editorial Board. I'm happy to announce the release of our annual magazine, Interface, the 2021 edition this evening. The IEEE Ed Board of JC are honored to have an esteemed panel of guests, advisors, and also our enthusiastic attendees to witness the release. Given the pandemic, the Ed team has been diligent in accommodating current affairs in STEM, such as COVID, and also has made new additions to the magazine, such as Getting Into Your Dream College, Georgia Tech, Tech Crossword, and Tech Quiz. I now ask Akshay and Dhanush to share and help release the magazine. Thank you, Dhanush.
So I think the presentation is gone. Can you once again present or share the screen?
Yeah, it's visible, right?
No, it's not. Suman? It was, but it's not now.
Okay, sir.
Yeah, Professor Roy, this is the IEEE interface, the magazine that we are saying. This is the covering sheet, and I think you will continue with the video. Sumant, I think some issue is going on with you. If someone else has this video, can you people just present that? If Sumant is facing some issue.
So we've shared the link on the chat, so anybody that does want to read it can access it through the link shared by Dhanush Srinath.
Okay, that's true. Okay.
Yes.
Yeah, please go ahead. Yeah.
Yeah. And until then, it is my pleasure to announce our release and congratulate all the editorial board members for playing an integral role, and also every other member of IEEE-JC for creating a safe and supportive environment to grow and expand our knowledge. Thank you, everybody that was present today and has borne witness to our release. We hope you like the changes we've brought in. We've made it more interactive this year, and let us know what you think. Thank you.
Yeah, thank you. Thank you.
Thank you, sir.
Yes, Srimad?
Yes, sir. So finally, we have Karthika Joyce to deliver the vote of thanks. Joyce?
Yeah, hello. Am I audible?
Yeah. Go ahead.
Okay. Good evening, everyone. I'm Karthikeya Joyce, Chairperson of the Electron Devices Society, SJCE. I would like to start off by extending my heartfelt thanks to Dr. Kaushik Roy, Fellow IEEE, Edward G. Tiedemann Jr., Distinguished Professor, Purdue University, USA. Thank you, sir, for taking time out of your busy schedule to talk and impart knowledge to us. I am sure that all of us here benefited immensely by listening to this talk. I want to express my thanks to the principal of JSS Science and Technology University, S.B. Kivade. Thank you, sir, for your presence here today. I would like to thank Dr. H.R. Mahadevaswamy, Joint Director, TED, JSS Mahavidyapita, for attending today's talk. I would like to express my gratitude to Dr. M.N. Jairam, HOD of the Electronics and Communication Department, JSS STU. Your presence here really means a lot to us, sir. Next, I would like to thank Dr. S.B. Rudraswamy, IEEE-SJCE EDS Staff Advisor, Commonwealth Fellow, Assistant Professor of the Electronics and Communication Department, SJC, JSS STU, Mysuru, for moderating this talk. We truly appreciate the efforts that you have made to make this talk possible, sir.
Thank you. Thank you.
All right, thank you very much. Certainly enjoyed talking to you all. Stay safe.
Thank you, sir. Thank you, sir. So, I also want to extend my grateful thanks to Dr. Sudarshan Patil Kulkarni, Vice Chair, IEEE Mysuru Subsection. Thank you, sir, for all your help and support in organizing this event. Next, I want to thank Dr. M.G. Veena, Branch Counselor, IEEE-SJCE Student Branch, for her presence here today and her continuous support to IEEE-SJCE. My thanks also goes out to all of the HODs, faculty members, and scholars who attended today's virtual gathering. We are grateful to you for attending today's talk. Finally, I want to thank the audience for their presence here today at this virtual gathering. With your continued support, we hope to bring you many such talks in the near future. Thank you.
Yeah, thank you, Karthikeya Joyce. So finally, I think we are at the end of this particular program. So I once again thank all the dignitaries, the faculty from other institute, our sister concern institute from Banglore, JSS Banglore, and JSS Noida, and all the other neighboring colleges of Mysore, and also there are many participants from across the state. Okay, so really, I hope this particular session was useful in inspiring you and motivating you. And you could see now how exactly the world is moving in terms of the technology. Okay, so with this, I think once again I thank Professor Kaushik. Right, it was really it was a great honor for us, sir. And really, thanks for accepting our invitation and delivering a wonderful talk. So we keep this interaction continuous. Okay, so we will be keeping in touch. And so I think last time we met was at IIT Bombay in 2012. It is 9 years. So there's a lot of difference that I can see in you. So anyhow, so we will try to be in touch, and you will be helping our students in a better way, sir. Thank you very much.
Right, thank you.
Yeah, so I thank all the management, the principal, and my colleagues of EC department helping out and participating in this. Thank you very much, and we will end this session. Thank you very much.
Right, bye-bye.
Thank you. Bye, sir.